Hello everyone, this is VPCB, your trusted PCB partner. Today our topic is the principles of impedance control, microstrip lines, and influencing factors. In today's high-speed digital circuits, it's not enough to simply ensure that a signal line can go from point A to point B. We also need to guarantee the quality of the signal during transmission. This brings us to a core concept, impedance control. Today, we will introduce impedance control for four-layer boards, helping you understand its principles and key influencing factors. Just like this PCB here, it also contains many parts that involve impedance and impedance control. Yesterday, we talked about differential pairs and length matching. Most of these differential lines also require impedance control at the same time. What is impedance control, and why is it so important? In AC circuits, impedance is the total opposition to the flow of current. In PCBs, what we pay special attention to is the transmission line impedance, also known as characteristic impedance. When the signal frequency is high enough, or the signal's rise and fall times are short enough, the wires on the PCB are no longer just simple connections. They start to exhibit transmission line characteristics. At this point, the propagation of the signal is like a water wave, and reflections will occur whenever there is an impedance mismatch. This is different from DC signals, where we can simply understand them as two states on and off or high and low levels. However, in the realm of high-speed electrical signals, that particular scenario is no longer the prevailing case. Instead, there will inevitably be some significant reflected states that can impact system performance. So why is impedance control important? First, it reduces signal reflection. If the signal source, transmission line, and load impedance are not matched, reflections will occur at points where the impedance changes. This leads to signal waveform distortion, such as overshoot, undershoot, and ringing, which seriously affects signal quality and can even cause data errors. It ensures signal integrity. Impedance control is the cornerstone of maintaining signal integrity. Stable transmission is the guarantee for reliable system operation. Let's take a look at a simple schematic. This is a simulation diagram. It shows how a signal with a rise time of about 1 nanosecond or less than 1 nanosecond behaves under different impedances. We understand that it should be a transition from a low level to a high level, with at most a gradual slope like the one at 40 ohms, where the rise is relatively slow. But in reality, we can see that when the impedance is 0 ohms, it's not a straight line. Instead, there's a long oscillation at the front end, which is caused by reflection. At 90 ohms, the rise time increases, so when the signal is fast enough, the effective high-level duration can be very short. That's why many circuits use a 50 ohm impedance, but in fact, the optimal value is actually a bit over 40 ohms. The concept and structure of microstrip lines. In multi-layer PCBs, there are two common types of controlled impedance transmission lines, microstrip lines and strip lines. Today, we will focus on introducing microstrip lines. A microstrip line is a conductor located on the outer layer of a PCB, usually on the top or bottom layer. It is adjacent to a large area reference plane, usually a ground plane or a power plane. As for microstrip lines in a four-layer board, our recommended four-layer board structure, which you should remember, is signal, G&D, power, and then signal. In this case, the L1 layer is the signal layer, and the top layer signal, together with the L2 ground plane, forms the microstrip line structure. The L4 layer is the bottom signal layer, and together with the adjacent L3 power plane or the L2 ground plane, depending on the order of power and ground, can also form a microstrip line. So what are the key factors that affect impedance? First is the trace width, which refers to the width of the signal line. Then, the trace thickness, which is the copper thickness of the signal line. In fact, it's the thickness of the copper on the surface. Next is the dielectric thickness, which is the thickness of the insulating material between the signal line and the reference plane. That is, the dielectric thickness between the L1 and L2 layers. Next is the dielectric constant, which is the dielectric constant of the material. This is a physical property that depends on the board material you choose, so when controlling impedance, you need to specify the material used to the manufacturer. Then there's the reference plane, which is the complete and continuous plane directly adjacent to the signal line. Let's now take a closer look at a typical structure to understand it better. This is an example in a calculation tool, SI9000, where you can see the length of a PCB and its structure. First, this H is the dielectric thickness we mentioned earlier. Then W is the width of the trace, which is this raised part. Essentially, it's the width of the signal line in the pin barrel flow. Next, T is the thickness of the trace, which is actually the copper thickness. And then there's ER, which is clearly written here. ER, also known as epsilon relative, is the dielectric constant. For any given material, it is a precisely fixed and unchanging value. As for their effects, the wider the trace, the lower the impedance. You can actually imagine it like this. The thicker the water pipe, the less resistance there is to water flow. Then the greater the dielectric thickness, the higher the impedance. The farther the trace is from the reference plane, the weaker the coupling and the lower the impedance. That is, the higher the dielectric thickness, the weaker the coupling between them, which leads to an increase in impedance. The greater the dielectric constant, the lower the impedance. The stronger the dielectric's ability to store charge, the lower the impedance. Then the thicker the trace, the lower the impedance. This effect is relatively minor, but we still need to take it into account when making calculations. Today we introduced the importance of impedance, understood the structure of microstrip lines, and learned how physical factors such as trace width, dielectric thickness, and dielectric constant affect their characteristic impedance. This forms the foundation for high-speed PCB design. In the next video, we will apply this knowledge in practice, learning how to calculate and control impedance in EDA tools, and mastering some basic techniques for determining trace width. If you enjoyed this video, please subscribe to my channel for more content. Thank you, everyone.